Okay, Unit 4, Equilibrium. All right, you've already done an introductory activity to start to explore the concept of a dynamic equilibrium. And we've learned that a dynamic equilibrium occurs when the forward reaction is occurring at the same rate as the reverse reaction. There will be some observable property, observable to your eye, so macroscopically, that remains constant. It might be the color of the solution or the mixture. It might be the size of the excess undissolved solute. We'll discuss some analogies and then go into specific types of chemical and physical equilibriums. Remember that the reaction must be reversible, so reactants form products and products form reactants, and we represent that with a forward and reverse arrow on top of each other. And this will only form, equilibrium will only be achieved in a closed system. So we'll look at those properties specifically when we look at physical and chemical equilibrium systems. For the moment though, let's think about and talk about some analogies. So imagining a hockey rink with nets at either end, center ice is in the middle here, and we'll have benches where the teams sit waiting, the players who are not on the ice are waiting to come on. So at any point you'll have 5 players on the ice, 5 skaters plus your goalie for each team. So I've just marked off one team here. Now, during the course of play, the referee doesn't have to blow the whistle for a change to occur. So if 2 players leave the ice, then 2 other players have to take their spot on the ice. So if you think about these changes happening, players are leaving the ice and players are going from the bench back onto the ice. So there's our dynamic piece. And in terms of equilibrium, as long as the rate of players leaving the ice equals the rate of players returning to the ice or going onto the ice, then the number of players on that team remains constant. So if you're sitting in the stands and you're looking out at the Leafs playing and you notice there's a goalie and 5 skaters, at any point in the game, it won't necessarily be the same 5 skaters, but there will be 5 skaters on the ice. And if there's more, then they'll get a penalty. That's not allowed. Okay, how about the idea of a teeter-totter? So let's say me and my twin sister are sitting happily on the teeter-totter, and that teeter-totter's quite balanced, so we're not moving. Do you think that's a fair analogy for a state of dynamic equilibrium? I'm going to suggest no, that there is a state of balance, this idea of balance, but there's nothing dynamic here. So we need something happening. We need a forward reaction, if you will, and a reverse reaction. So I would say that this teeter-totter is not a good example or analogy for dynamic equilibrium. I love this. I love running up the down escalator in the mall. Now, I realize that's probably not a safe thing to do, so I'm not recommending you go out and do it, but if you've ever done it, you know it's kind of fun to try to get to the top. So that escalator is moving down, and of course you are running up the down escalator. So first you get on and you try to figure out the speed of that escalator, and at some point you match the speed of the escalator as it's coming down. You're running at the same speed going up, and maybe you match that, at like early on in the escalator, like maybe down low, or maybe down here, or maybe in the middle, or maybe up at the top. But at some point your rate equals the rate of the escalator, and at that point you're in a state of dynamic equilibrium. And you'll know it's dynamic because if you stop running, you lose that equilibrium position. Or if the escalator stops, then you'll lose that equilibrium position. Okay, so I challenge you to think of your own analogy and be ready to share that with the class. Okay, specific examples of physical and chemical equilibrium systems. So the first two we'll look at are physical equilibrium systems. For example, solubility equilibrium. So we're looking at a crystal or solute added to water, and we're representing that by the equation XY solid forms the hydrated ions, X positive and Y negative. I've drawn some pictures below here to help understand what's happening. But first, let's label or describe the forward reaction. So what term would you give to describe XY dissolving into those ions? Hopefully you're thinking dissolving or dissolution, if I'm going to do the noun. And what do we call the reverse reaction when the ions reform the crystal? Well, that's called recrystallization. So at equilibrium, the rate of that dissolution will equal the rate of the recrystallization. So we said for dynamic equilibrium that the forward and reverse rates will be equal at equilibrium, and we said there'll be an observable macroscopic property that is holding constant. Can you figure out what that is in a solubility equilibrium? You can pause the video and think about it, and then I'll go through these diagrams here and see if you can figure it out then. Okay, so when we first put a solute in water over here in beaker A, then that solute begins to dissolve. And so the rate of dissolution is the forward rate's the only one that's happening. Now, as that substance dissolves, this size of solute gets smaller. So you can see I've shown it smaller. And at that point, we've started to have ions form in the solution, right, from the forward reaction. So we'll still have the dissolving happening, right, but we'll also start to have recrystallization happening. So those ions are recrystallizing. What's going to happen to the size of the solute? Maybe I'll go here, right? When the number of ions leaving the crystal lattice becoming hydrated is equal to the number of ions recrystallizing. So here's where the rate of the forward reaction equals the rate of the reverse reaction. This is our state of dynamic equilibrium. So in the first two, A and B, we're not at equilibrium. In C, we are at equilibrium. Now, there's one subtle, and what is the observable macroscopic property remaining constant? Hopefully you're thinking the size of the excess undissolved solute. You'll notice it was getting smaller and smaller from A to B to C, but now at C, when the rate's the same, if two crystals dissolve and then if two ions dissolve and two ions recrystallize, then that size of that excess undissolved solute, right, remains constant. So for solubility equilibrium, we always write the solid on the left side of the arrows, the double arrow, the ions on the right. The rate of dissolution equals the rate of recrystallization at equilibrium, and you'll know that because the size of the excess undissolved solute is not changing. Now, just a comment, because I left this system open in terms of the water, I didn't actually put a lid on that beaker. It would make more sense to have put a lid on that beaker, because certainly if that water is allowed to escape, that will throw off this solubility equilibrium. So let's explore that phase equilibrium of water liquid forming water vapor. So when water liquid forms the gas, we have evaporation, and when the gas reforms the liquid, we have condensation. So if you leave a beaker of water open on the counter, it will evaporate. And as long as that system is open, it's never going to reach equilibrium. We can't have the condensation happening if we leave the system open. so the water level drops. Now, if we were to cover that beaker, now as the water is evaporating and forming water vapor trapped by the lid, we'll start to have the condensation occur. So the water level will drop a little bit more, and then we'll reach the point where the rate of water molecules leaving the liquid state, moving up to the gas state, equals the rate of condensation. And at this point, we're at equilibrium. So here's where the rate of evaporation equals the rate of condensation. And what macroscopic property observable to your eye is remaining constant? Hopefully you thought the water level. And yes, the water level remains constant. So this, of course, is the necessary requirements for a system to be at equilibrium. Okay, so those were two physical equilibriums. Now we look at chemical equilibrium. So you'll see that I've drawn three circles here. Equilibrium is the black circle, which I've labeled underneath. The idea is that on the left in the blue, we have 0.1 moles of NO2 in 0.5 liters. So I'd just like to refresh your memory here that moles is N and volume is V, and that we calculate concentration by doing N over V. So can you see where I got the 0.2 moles per liter of NO2? The fact that we have 0.1 moles in 0.5 liters. So 0.1 divided by 0.5 will give us 0.2 moles per liter. So I'm always doing this calculation with the moles and the volume to get the concentration initially. So I drew some NO2 in the flask here, and you'll notice I didn't put any N2O4. Therefore, the initial concentration of N2O4 is 0 moles per liter. Now, as these NO2 particles start to react, and I'm going to mark this up a little bit, but as the NO2 particles start to react, the balanced equation is this: 2 NO2 form the N2O4. So 2 of these are going to form an N2O4. Okay, and 2 more are going to form an N2O4 molecule. Now, as that N2O4 starts to increase in concentration, the reverse reaction will occur. So this is a chemical system where the forward and reverse reactions occur in a closed system. So those N2O4s will start to decompose and we'll go back to having 2 NO2s. At equilibrium, so at the point where the rate of the forward reaction equals the rate of the reverse reaction, the concentrations are provided here in black. So you'll notice at equilibrium that the NO2 concentration is 0.12 moles per liter. So it started off at 0.2 and it's dropped down to 0.12 moles per liter. So we do have some NO2 in the flask, right, corresponding to that 0.12 moles per liter. So I'm just putting 4 of those in just to show that there's NO2 in the flask at equilibrium. Now, is there N2O4 in the flask at equilibrium? Yes, there is, but not too much of it, right? 0.04, so maybe I'll just put 1 of those in there. So I'm just putting the number of particles in, indicating the relative amounts. You'll see that's a greater concentration than here. Okay, now, what if we had started, instead of the blue situation on the left, what if we had started with only N2O4 in the flask? So, if we had started with 0.05 moles of N2O4 in a 0.5 liter flask, again, remembering concentration, C equals N over V, where this is N and this is V, you'll notice down here that the concentration of N2O4 initially is 0.1 moles per liter. That's coming from the 0.5 divided by the 0.5. And I don't have any NO2 in the flask to start with. So, what's going to happen when you look at this reaction? If you only have N2O4, the reverse reaction is going to occur to start. And so an N2O4 is going to decompose into 2 NO2 particles. And that will continue, right, until those NO2 particles start to increase in concentration, and then the forward reaction will start to occur. And those NO2 particles, right, 2 of them will reform an N2O4. And so the forward and reverse rates occur, right, and keep occurring, but eventually their rates are equal. And at the point where the rates are equal, we've reached equilibrium. And it turns out that if you start with 0.2 moles per liter of NO2 or 0.1 moles per liter of N2O4 with none of the other reactant in the flask, you'll eventually achieve equilibrium, and the concentrations will be 0.12 moles per liter for NO2 and 0.04 moles per liter for N2O4. And so you can see here that equilibrium can be reached from either direction. It's important also to notice that the concentration of the NO2 does not have to be equal to the concentration of N2O4 at equilibrium. It is the rate of the forward reaction that equals the rate of the reverse reaction. This concentration of 0.12 moles per liter will remain constant at equilibrium, but it does not need to be equal to the concentration of the N2O4 at equilibrium. Okay, let's take the data from those two equilibrium systems and communicate those in an ICE table and in a graph. So for the ICE table, you'll see the letters I, C, and E. So I purposely write the balanced equation, and then I label my rows I, C, and E. I stands for initial, C stands for change, and E stands for equilibrium. Okay, so considering the situation on the left, the concentration of NO2 initially, so you'll see I had that right up here, the concentration of NO2 initially is 0.2 moles per liter. And I'll just remind you that that calculation came from the calculation of N over V. We had N divided by V, and so when you're doing word problems in the textbook, you can expect to take the moles and divide by the volume in order to determine the concentration. And so here we have 0.2 moles per liter. Concentration of N2O4 initially is 0. Now, the picture on the blue, right, eventually became an equilibrium system, which now we're given the concentrations at equilibrium. So we can see the concentration of NO2 at equilibrium is 0.12. So I come down to the equilibrium row, and underneath NO2, I fill in the 0.12, and then 0.04 moles per liter for the N2O4 concentration. So what do I fill in the change row? Well, how did 0.2 moles per liter here become 0.12? Did this initial concentration increase or decrease as it approached equilibrium? Hopefully you're thinking it decreased because the number dropped. And how much did it drop by? 0.08. Okay, how about on the N2O4 side? It started off at 0 and at equilibrium had 0.04 moles per liter. So how much did this increase by? And hopefully you're thinking 0.04. And so you can see here that I've indicated I plus C equals E. So 0.2 minus 0.08 equals 0.12, and 0 plus 0.04 equals 0.04. I'd also like to point out that the change row, that the amount of NO2 that's dropping is actually double the amount of the N2O4 that's increasing. And notice that that ratio, that this is double this amount, is consistent with the mole ratio of 2 to 1. And so that's another important point, is that the change row will occur according to the coefficients in the equation. So it will follow the mole ratio. Okay, see if you can complete the table on the right, the ICE table, for the situation from the picture in red. Okay, hopefully this is what you came up with. Again, my initial concentrations were stated here in red. The equilibrium concentrations are from the diagram in black ink, and I've constructed my ICE table accordingly. Does it seem that the change row is following the mole ratio of 2 to 1? And hopefully when you look at those values, 0.12 and 0.06, you realize that yes, 0.12 is double the 0.06. So again, consistently the change row, your values there will follow the mole ratio. Okay, now let's represent these graphically. So I want to plot on the left side the table from the ice table on the left. So initially the concentration of NO2 is at 0.2. So maybe I'll mark this. This will be 0.2 here. And it finishes at 0.12. So I'm going to say that it starts here and finishes maybe about here. And so I show the graph decreasing and then plateauing. So the plateau is where the equilibrium concentration has been reached. So this is NO2. How do I represent the N2O4? Well, it started off at 0, so I'm down here at 0, and I need to go up to 0.04, so maybe this far. So there's my N2O4. Okay, the graph on the right, perhaps you can try that one from the ice table, build your graph, and then check with the video. And so you can see that I started the NO2 at 0 and had it finish at about 0.12, and the N2O4 started at 0.1 and plateaued at 0.04. And so you can see the equilibrium has been established probably from about this point on in each graph, and you should see the plateau. Okay, the last part of the video is the concept of equilibrium position, and it represents the relative concentrations of reactants and products at equilibrium. So when you think of running up that down escalator, and we spoke about this in class, the idea that as the escalator is moving down, you may match the escalator's speed near the bottom, in which case your position, if somebody's watching you, you're kind of holding still right about there. But maybe you don't actually match the escalator's speed until you're holding in the middle position of the escalator. Or perhaps you go all the way to the top and your position holds up here, and that's the point where your speed matches the speed of the escalator. And so we can have different positions or different relative amounts of reactants and products at equilibrium. So let's look at that in the context of the possibilities that can occur. If reactants are forming products, as you can see in this equation, one option, option A here, is that the reaction proceeds to completion. In other words, really, I'm better to just write a single arrow forward. There is no reverse reaction. We would say that the equilibrium position, so again, the relative amounts of reactants and products, there would be no reactants and a great deal of products, so we would say that the equilibrium position lies far to the right. Sorry, that wasn't very neat there. I don't know what happened with the pen. There, far to the right. Or we could say it heavily favors the products. So in terms, if I did a bar graph here to represent the amount of reactants and the amount of products, then I would have a huge amount of products and no reactants. Okay, now what's another option? Well, an equilibrium could be established for a reversible reaction in a closed system. So let's say that the position lies to the right, and I'll talk about the value of K in tomorrow's lesson. But let's say the position lies to the right, not far to the right, just to the right. In that instance, we will have some reactants, but we'll definitely have more products than reactants. So the height of the bar graph is representing the amount of products, and you can see that there are more products than reactants at equilibrium. K really comes from taking the products and dividing by the reactants. So can you see how the one product bar graph divided by the reactants would produce a value that's greater than 1. Now, what if the concentration of the reactants and the products are essentially equal? Wouldn't K then be equal to 1? And that's when we say the equilibrium position lies in the middle. Now, in the third case here, what if we have more reactants than we do products at equilibrium? Well, here's where the value of K being that it's always products over reactants, that numerator is going to be lower, and so that's where we would have K being less than 1. So I'll talk more about K in the second lesson, but you can see that the ratio of products to reactants is changing. In this instance, the ratio of product to reactants, right, the products are taller, so our numerator is larger, we end up with a value greater than 1. Here they're equal, so we end up with a quotient equal to 1. And here the products are less, so we end up with a quotient less than 1. K is less than 1. The final option here is that the reaction does not occur. And when I say that, I mean in the forward direction. So, for example, reactants, we put an arrow and then we say NR, there's no reaction. We would say that the equilibrium position lies far to the left. The idea here is that it heavily favors the reactants. So in other words, at equilibrium, or really the equilibrium's established, really there isn't a forward reaction. So we don't have any products forming. So the idea is that we have all reactants and no products at equilibrium, which really is the case when the reaction does not occur in the forward direction. Okay, so important concepts today. The concept of dynamic equilibrium. The concept of being able to represent these in ice tables. We also looked at graphs, which ties into your bean activity in class, and we looked at the concept of equilibrium position. You will see these 4 concepts repeat throughout the unit, so I encourage you to try the textbook work, ask questions, and come up with your analogy. We'll talk further about those in class.